So we are going to move into chapter 8. And we are going to start with basic probabilities. So in order to talk about probabilities, we do have to talk about what is a sample space. The sample space is the set of outcomes for an experiment. Each trial of the experiment yields only one outcome. So again, this should be reviewed from statistics. Remembering that in a sample space, every single individual probability has a value between 0 and 1, inclusive, meaning the probability can be 0, the probability can be 1, or any value in between. And if you sum all of the probabilities in the sample space, you must get a total of 1. So this is an example. If I were to take 2 coins and flip them, your potential outcomes are to get 2 heads, to get a head and a tail, to get a tail and a head, or to get tail and tail. That means your sample space is all of those outcomes contained in curly brackets. So the curly brackets, again, is the set. And this is then the set of all the outcomes that happens when you flip 2 coins. So then they can ask you different questions, like what represents the event of a head first? Well, if I look at this, I have 4 potential outcomes. So head has to be the first thing that comes up. That happens in these first 2 outcomes. Head, head, or a tail. Which of those 4 outcomes represents the event one of each? Meaning I have to have a head and I have a tail. Well, that's head, tail, or tail, head. We have to know the entire sample space. We have to know an account of how many times a specific event occurs to be able to determine a probability. So anytime we want to find a probability, the probability of any event is the number of ways that that event occurs, divided by the total number of outcomes. So if your event happens 5 times and there's a total of 20 outcomes, your probability would be 5 out of 20. And then you could reduce that as a simplified fraction of 1/4, or you could turn it into a decimal. 1 divided by 4 is 0.25, or you could turn it into a percent. So any of the 3 options, a fraction, a decimal, or a percent, all are okay when talking about a probability. One way we see probabilities is with a deck of cards. So if you are not familiar with a full deck of cards, there is an image of a full deck of cards on the upper right-hand corner of the slide here. So if you're ever asked a question about something that you're maybe not 100% familiar with, or you're like, I don't remember how many of this there are, go look up a picture of it, or go back to my PowerPoint and look up the picture here. So in a deck of cards, we have 52 different cards. First question says, what is the probability that I were to get a red? Well, one way to think about this is to actually count how many reds there are, right? So there are 26 reds out of 52 total cards. So I could have counted this. That would have been 13 in this row and another 13 in this row. Gives me a total of 26 out of 52. That is equivalent to a half. Now, the other way I could have done that a lot faster is if I had just looked on the right-hand side here. Do you see that half of the cards are red and half of the cards are black? Yes, there's only two colors. They are red and black, and they occur in the exact same frequency, so probability of red is a half. Next one says the probability I draw the ace of diamonds. Well, the ace of diamonds is this one singular card out of the total 52. So done. Can't simplify that. Next one says the probability of a jack or a queen. Well, there are 4 jacks, and we talked about on Thursday, remembering that or means we add. There are 4 queens. So 4 jacks or 4 queens is a total of 8 cards out of the 52 cards. That will simplify to 2 out of 13. Now, the reason it simplifies to 2 out of 13 is there are 13 distinct cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. That's 13 different types of cards. You've selected 2 of those 13, jacks or queens. So if I just want the probability of a jack, we go back, there were 4 out of the 52, which is 1 of the 13 different types of cards that I could get. And then last question on the cards here says not a face card. So this is the complement of a face card. Not a face card would mean the probability of face not, face complement. So if I look at it, face cards are the cards with persons or faces on them. So that's the jacks, queens, and kings. They have images of people. They have a face. That's why it's called a face card. There are 12 face cards. So if I don't want a face card, I want the remaining cards. So I could take 52 minus 12, tells me there's 40 remaining cards that are not these 12 face cards out of the 52. Okay, the other way I could have looked at this is these were 3 of the 13 different potential cards. So what's left is the remaining 10 out of 13. 40 over 52 does reduce to 10 out of 13. Generally, I will leave mine in fractions just because sometimes they don't divide nicely into a decimal. So I don't want to round. I'll just leave it as a fraction. But if you wanted to put it in a decimal or a percent form, I wouldn't mark it wrong. All right, so let's pretend we are playing with a game that has a spinner. There are 15 total sections in this spinner. 6 of the sections are red, 5 are blue, 3 are yellow, and 1 is green. So the first question says, what is the probability I get a blue? Well, if I look at this, it says there are 5 blue. So 5 out of the total 15 are blue. And I can reduce that to 1/3. 5 and 15 are both divisible by 5. 5 divided by 5 is 1. 15 divided by 5 is 3. That's how I got the 1/3. The next question says probability of not red. So you have 2 choices. You can find the probability of red and subtract it from 1, or you just count up everything else. So we know 6 are red, meaning 9 are not red, because those 2 have to sum to the total of 15. 6 and 9 make 15. So 9 out of 15 are not red. These are both going to be divisible by 3. So 3/5. Probability I get yellow or green. So remembering, or says I'm just going to add those outcomes together. There are 3 yellow 1 green for a total of 4 spaces out of the 15. This one does not simplify. And the last question for this one says the probability of purple. Is there a purple section in our spinner? No. So what does that mean our probability is? 0. It cannot occur. A probability of 0 means it cannot occur. It is impossible. It is not a part of this set. Any or all of those work. Another common example here, if you took my class, you've seen this chart before with this sum of 2 dice being rolled. I always like to pick a dice table that has 2 different colors so you can distinguish between which die is rolling which number. Because it's a different outcome if the red die rolls a 3, the green die rolls a 1, is different than 1 is on the red, 3 is on the green. They are technically different. The nice thing about these dice tables is that any specific sum you're looking for can be found along a diagonal. So here's the sum of 2. Here's the sum of 3. Here's the sum of 4, the sum of 5. All the diagonals going from a left up to a right on a diagonal make the same sum. So if I want to find sum of 8, well, that's 6 and 2, 5 and 3, 4 and 4, 3 and 5, 2 and 6. So all I have to do then is that's 1, 2, 3, 4, 5 of my outcomes. And our total is we have 6 outcomes times 6 outcomes, a total of 36 in our table. So sum of 8 happens 5 out of 36 times. The probability of sum is 1. Can I get a sum of 1 if I roll 2 dice? Y'all are shaking your heads. No. So not possible. It is 0. All right, next one. The sum is divisible by 5. So I'm looking for numbers that when I add the 2 dice together, I get a number that is divisible by 5 nicely. So what numbers can I divide by 5 nicely? 5 and 10. Yes. All right, so my sum of 5s are happening here. And my sum of 10s are happening over here. So that was 1, 2, 3, 4, 5, 6, 7 of them that I marked off there out of my 36. Next one, probability I do not get a double. So again, I always like to count the ones that are that and then subtract them out. So doubles are these guys: 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So doubles happen 6 out of the 36 times. If I don't want the doubles, I want what is left. So if I've used 6 of the 36, yes, there are 30 remaining of the 36. So is not doubles. So if you ever add a probability and its complement, you should create the whole 36 out of 36. All right, next one. Let's see, orange here. Sum is odd. Okay, well, this is a sum of 2, so that's not going to work. These ones are sums of 3, so that'll work. Next one is 4. So I'm going to do every other diagonal here. Skip this one, then I do the next diagonal. Skip that one, and then I do this diagonal, and then I do this one. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 out of 36, which is a half. And that should make sense, right? Half of the numbers we're working with are odd, half of the numbers we're working with even. So we should end up, when we add them together, half are odd, half are even. And our last question, the sum is bigger than 1 or smaller than 13? So first question, do I have anything less than 1? No. Do I have anything bigger than 13? No. So what have I used? All of them. If I've used everything, what is my probability? 1. Beautiful. That's a typo. What if we do more than one event? So I want to draw 5 cards from a deck of cards. What I can do is I can use the combinations that we did on Tuesday to help me with this. We talked on Tuesday about it was the Jack and Queen problem. And we said in the beginning, we had 52 cards that we chose 2 from. And that gave me like 2.5 million. 52, choose 5, not 2. 52, choose 5. So it was 2,598,960. That's my denominator for every single one of these problems. Anytime I'm drawing 5 cards, this is the total number that I have ways of drawing 5 cards from a deck of cards. So the denominator of all of these is 52, choose 5. The top is then going to be, what am I drawing? I have 52 cards, or do I have 52 cards? What am I working with here? I want to get 5 red cards. Well, how many red cards are in the deck? We go back. We said red back here. There were 26 red cards. So I have 26 red cards. How many of those am I choosing? 5, because I want 5 red. So I want to take 26, choose 5, and then divide that by that 52, choose 5, or that 2.5 million value that I have over here. So these are ones I definitely use a calculator for. I do not attempt to do these by hand. And these ones most likely will end up in decimals just because you are using technology here. So it was NCR got me my function 26, 5. And I'm going to divide that by NCR 52, 5. In a game of poker, you actually only have about a 2.5% chance of drawing all red cards. 5 red cards. Only a 2.5% chance, because 0.025, if I times that by 100, turns it into the percent form. So that moves the decimal 2 places over, 2.5%. So usually when I'm doing these, I round to like 3 or 4 decimals. 0.253. Next one wants no diamonds. So we know our denominator is staying the same. So if I go back here, I don't want the diamonds. So that leaves 3 rows of 13 cards, a total of 39 cards that I do want to draw from. So I'm drawing from 39 that I want. I'm taking 5 of them. Now, we would expect, because I have more cards to work with, my probability is going to be a little bit larger than it was for the last one. So I'm just going to go up here and change that to a 39, just so I don't have to retype everything. And you can see definitely a lot more likely for that to happen. This is about 22% of the time. So 0.2215. Oops. I could get a 5-card hand that doesn't contain a diamond. Next one asks for the probability I get 2 clubs and 3 diamonds. So and implies that we are going to multiply these 2 pieces together. So we have 13 clubs, of which I want to choose 2 of them. I have 13 diamonds, of which I want to choose 3 of them. I'm going to multiply those 2 values together because it says and. And then it's going to be over the 52, choose 5. I will have to retype this whole thing. CR 13, oops, 13 and 2. All right, I'm gonna put my divide symbol, no, wrong button. All right, just so I can get my denominator so that my whole numerator is together. Times NCR 13.3 is over NCR 52.5. Now, you should always have the second value. So here, 5 and 5, those should match. So if you have more than 1, 2, and 3, make a total of 5, 5 out of 5. So I know I'm at least getting the same amount, that I've set it up correctly. This one is 0.008. It's going to round to a 6. The 8 after the 5 rounds the 5 to a 6. So 0086. So less than a 1% chance that I would get 2 clubs and 3 diamonds. And that would be the same for any 2 suits. Okay, so if I picked 2 diamonds and 3 hearts, would be this exact same percent, 0.0086. If I picked 2 spades and 3 clubs, 0.0086, because there's 13 of each suit. All right, our last one here, probability I get 2 kings and 3 aces. So there are 4 kings, of which I want to get 2 of them. There are 4 aces, of which I want to get 3 of them. So I've drawn my total 5 cards. 52, choose 5. And this one, again, thinking about it, should have an even smaller percent than the previous one because I'm only working with totals of 4 instead of totals of 13. So we go here. I'm going to change this one to 4 and 4. And yeah, 1, 2, 3, 4, 5. I'm going to have to go to more decimal places to be able to write this. 5 zeros and a 9. 1, 2, 3, 4, 5, and a 9. Very, very, very unusual to get a full house of kings and aces. We have one more situation we're going to work with. This is on Blackboard if you wanted to pull it up, or you can just kind of write down the quick specifics here. We have a Math 110 class at a junior college that must select 3 students to serve on an advisory committee to the dean. Okay, so our goal is we are choosing 3. That's our goal. We have 16 freshmen and 14 sophomores. So we have a total of, that makes 30. So we have a total of 30. We know we have to choose 3. They're going to ask us some different questions about that. And guess what? The first one is, how many ways can I just choose 3 from the class? Okay, no specifics other than they just have to come from this class. Well, there are 30 students in the class, and I want to choose 3 of them. Okay, so you could go to the Desmos calculator. It is going to give you the value of 4,060. So there are 4,060 different ways to select 3 students from 30. What if we want to choose only freshmen? How many 3-person committees can be chosen from the class if the committee consists of only freshmen? Well, what now is my starting value that I am choosing from? How many freshmen are there? 16. So I have 16 that I want to choose my 3 from. So if I take 16, choose 3, that can happen 560 ways. Now I'm going to ask the other grade here. It says how many 3-person committees can be chosen from the class if the committee consists of only sophomores? Okay, so how many do I start with? How many can I choose from? 14. I'm going to again choose 3. If I do that, I will get 364. I hope it's okay at this point that I'm not showing you how to type this into Desmos because we practiced that last week or last class. Sorry. Next one. How many 3-person committees can be chosen from the class if the committee consists of 2 freshmen and 1 sophomore? All right, so I'm going to put that up here. 2 freshmen and 1 sophomore. So I want to choose 2 from the 16. 16, choose 2. And means I'm going to multiply that by, there are 14 sophomores that I want to choose 1 from. This one is going to give you 1,680. Now, if we're going to use all of these to then turn them into probabilities or percents. So I'm literally going to go through now and ask you, what's the probability of getting such and such? Yes. Question was, why didn't we divide yet by this total 30, choose 3? Because the question is not asking what's the probability yet. So anytime it says how many, you're only looking for the numerator. Okay? Or in this case, when you find all of them, this is actually going to be the denominator for all of them. So if this is a specific one of only freshmen, I could then find, and it's the next question we're going to ask, the probability that I pick only freshmen will then create the fraction with these 2 values. Yeah, so how many just means do the combination part. When you see this part, what's the probability? And then you're going to divide, then you're going to have a value between 0 and 1. So the probability that it's all freshmen. Well, we said 560 were freshmen, and our total was 4,060. That's this one here. Okay? All the ways that this can be done from the total of 30 is 4,060. All right, that comes out to roughly 0.1379. What if I want to get all sophomores? Well, all sophomores was this one, 364 out of 4,060. And again, I'll round it as best as I can, 0.897. You can just leave them as the fractions too. I don't really care. We found how many ways 2 freshmen and 1 sophomore were chosen. That was here. How many ways 2 freshmen and 1 sophomore happened was 1,680 times out of the 4,060. I divide that, about 4,138. Now they're asking us for one other option that we didn't find, 1 freshman and 2 sophomores. So let's go back here. we want 1 freshman and 2 sophomores. So let's flip these. That's 16 choose 1 and 14 choose 2. And that one is going to give you 1,456. It gives you 16 times whatever this value is here, and total of 1456. So the last one is going to be 1456 out of 4,060, or roughly 0.3586. So then the last part of this says, find the sum of the probabilities in all 4 of these parts. So 560 out of 4060, 364 out of 4060, 1680 out of 4060, and 1456 out of 4060. Now, when I add fractions, I keep the denominator the same. It's kind of like your label. The way I always try to describe it is like if I had 1/4 plus 2/4. So if I simplify it here, 1/4, this is red as a quarter, plus 2/4. How many quarters do I have now? 1/4 plus 2/4 makes 3/4. I didn't change my label or my denominator. So every time we add fractions, our denominator is going to stay as it is. And if I sum 560, 364, 1680, and 1456, guess what? I get 4,060. Why? Why did I get my total? I've done every single combination. Okay, the only way I could do this is all freshmen, all sophomores, 1 freshman with 2 sophomores, 2 freshmen with 1 sophomore. No freshman means all sophomores. We've accounted for every single possible grouping, so we've totaled our total. Exactly. All outcomes accounted for. So this is an example here of a probability distribution, because you have all the individual probabilities that can then sum to our total of 1.